Good morning. Well, here we are. We are at chapter 39. We're going to start looking at the quantum mechanics of atoms, and we're going to look at this at pretty good level of detail. So we're going to get a pretty good idea of what's the basic quantum physical principles that we work from in understanding what's going on inside atoms and molecules. And let's take a look. So here's one way to think about what everything is made out of. You know, often we say everything's made out of atoms and molecules. Well, atoms and molecules are really combinations of nuclei and electrons. Now the nuclei, at least for purposes of this chapter, we can think of the nucleus as a point charge. So the nucleus, if I've got a collection of molecules, if I look at all the nuclei in the molecules, they're all just these positive point charges because the nucleus is so small compared with the size of the atoms and molecules. The size of the atoms and molecules really comes down to electrons. There are electrons. The probability distribution of the electrons is what fills all of that space in atoms and molecules. So in chapter 39, that's what we're looking at. We're looking at atoms. And for the most part, what that means is we're looking at the quantum states, the possible quantum states, the wave functions, the probability distributions of the electrons. How are the electrons arranged? And how much energy do those electrons have? Now, if we look at the simplest example of an atom or a molecule, that would be the hydrogen atom. That would be a proton surrounded by an electron. So again, the idea now is that the electrons are probability distributions. Their wave functions are spread out over the entire volume of the atom, and as are the probability distributions. Now, where this is all coming from, we're going to be able to go in and take a look at the hydrogen atom. Again, it's the simplest case. It's a single positive point charge surrounded by one electron. What are all the possible wave patterns that an electron can have surrounding a proton? To answer that question, we would go back to the Schrödinger equation. Now, the Schrödinger equation in the previous chapters, if we go back to, I guess it would be going back into chapter 38. In chapter 38, we looked at a three-dimensional example. What we said was the kinetic energy of the electron, the kinetic energy of a particle, could be represented as 1 over 2m times the momentum components squared. So px squared plus py squared plus pz squared. What's different in chapter 39 is we are introducing a more subtle, a more accurate potential energy expression. So instead of just saying there's a region and the electrons are stuck inside that region, we are now introducing the electric potential energy. The potential energy due to the electric interaction between the proton and the electron. Now, typically we talk about this as being electric magnetic. There are magnetic interactions, but they're not the largest effect. So the largest effect that we see is understood in terms of this potential energy term, which if you remember from chapter 23 or whatever, that represents the potential energy between two point charges. Now, clearly the proton here can be represented pretty well as a point charge. What about the electron? Well, what's going to happen here is that we're going to take this energy statement and turn it into a Schrödinger equation. So all of this momentum stuff is going to turn into some partial derivatives of a wave function. And the wave function is also going to show up on the potential energy term. And so what this wave function next to the potential energy does is it keeps track of all possible locations. It says, okay, if the electron's here, how much potential energy is that? If the electron is here, how much potential energy would that be? Over here, over here. And so what it's doing is it's sampling all the possible locations and reporting back how much potential energy that would correspond to. And it's saying that in each location we look at, the energy of the wave function is going to be represented by a set of momentum calculations at that location and a set of potential energy. These momentum calculations combined, momentum squared, is going to give us kinetic energy. So, you know, you always say, does that look like kinetic energy? And I guess once you work a few of these problems, you go, yeah, that's what kinetic energy looks like. This is what potential energy looks like. And now we're using the correct potential energy formula for two charged particles. All right, now this is in rectangular coordinates. This is in terms of x and y's and z's. That's not a good set of coordinates to work in terms of for atoms. We should really be working in spherical coordinates. That's going to give us a better representation. So we're going to move away from rectangular coordinates into spherical coordinates. Now, I'm not sure how much background you guys have. You know, I'm sure it varies from within the class of working in spherical coordinates. And the first thing to realize is, I'm going to say don't worry about this. We will try and provide some backup, some support to help describe what we need to understand. Now, taking a bunch of derivatives in rectangular coordinates and converting them into what are called spherical coordinates, it's complicated. And no, you guys don't have to worry about this. So what we're saying is that this stuff, there should be some familiarity making the connection with x, y, and z components of momentum and the partial derivatives here. But this is really complicated. This is keeping track of directions in terms of r and theta and phi. And those are, little r should be pretty familiar. So little r is saying, you know, placing the proton at the center of a coordinate system and saying little r measures the distance out to any location. Now, in addition to little r, I need a couple of angles. Theta, and we'll see some more, we'll come back and look at this, I think. But if we define a z-axis, a vertical axis, theta is measured relative to the z-axis. So if you're familiar with latitude and longitude, which I hope you guys are, so lines of latitude, theta is kind of like latitude, except that instead of theta being measured from the equator outwards towards the pole, theta is measured from the North Pole to the South Pole, or from the positive x-axis to the negative positive z-axis to the negative z. Let's say it that way. And so theta can go from 0 to pi radians. Now, phi is measured in terms of longitudes. So if I'm going to measure a circle along some latitude line, those lines of longitude are going to run from all the way around from 0 to 2 pi, or from negative pi to positive pi. I need to think in terms of all the way around a complete circle, whereas in latitude, we don't have to do that, because once I have completed halfway around the circle in latitude, I've accounted for all the possible latitudes. Okay, so that's how spherical coordinates work. Again, if you didn't catch all of that, I'm going to say don't worry at this point. There's going to be more representations of this in the textbook. We'll look at this in some more examples. But the first thing is to show that it's complicated really fast. This is why we've spent kind of, a couple of chapters preparing for this. And now we're going to take a look and at least carry out a few examples. Now, these hydrogen quantum states, they're going to be represented by what we call quantum numbers. Oh, here's our coordinate system right here. So if this is the xy plane running this direction, and this is the z-axis, as we were saying, theta starts at 0 at the positive z-axis, and then as an angle it comes down. Now by the time it gets to the xy plane, theta has reached pi over 2, 1/2 pi, or 90 degrees, but we're going to be working in radians. And so actually we're not really going to be working in any units. We're not going to do a lot. We're not going to do calculations in terms of these angles, but this is going to come down to 1/2 pi, and then continuing on to the other half of the sphere would go all the way to pi. Phi, on the other hand, comes from looking at the xy plane. So this is actually xy, and phi starts at the x-axis and then increases, well, the way you've seen in your math classes. So in math classes, you've seen angles defined in the xy plane. So phi, I'm hoping, is a little more familiar. But theta is the one that's probably a bit new. So we're going to end up with, when we solve that three-dimensional Schrodinger equation, so that's the equation we're solving, we want to have a wave function that when we take all these different derivatives and multiply by all these different factors, that the side on the left of the equation matches up with the stuff on the right side of the equation. And there's only certain wave patterns for which we can find a solution. And those wave patterns are going to represent the quantum states of the electron. And that's apparently how nature works. So this one equation right there, that Schrodinger equation that we've written down, makes a series of predictions about all the possible wave patterns. And when we look at those, that is what we see in atoms. So apparently that one differential equation describes the properties of the electrons, all the possible quantum states for the electrons inside atoms. Now it turns out that electrons in atoms, it's more complicated than just energy. So this is an energy formula that Bohr developed, making some really basic assumptions about how electrons would work, and the assumptions that really don't work. But he was able to find his way to a formula that actually correctly predicted the energy of the quantum states. Now, with the Schrodinger equation, we're going to say this is the correct way of solving for that energy formula. When we solve this equation, this is the energy formula that we get. It actually comes from that equation. So here's the energy. This is the mass of an electron. This is the electric magnetic force constant. This is the fundamental charge, the charge on a proton or the charge on the electron. And that is Planck's constant divided by 2 pi. That is h bar. And that's it. That's what the energy formula depends on. There's a series of quantum states that can be characterized by a quantum number. And the quantum numbers can actually just be written as a series of integers, successive integers, where n starts at 1 and then continues on to the values of 2, 3, 4. Where does that pattern come from? It comes from solving that equation. So every time we say it comes from solving the Schrodinger equation for the electron inside hydrogen, it's coming back to this. This is kind of deriving the Schrodinger equation that would apply for the electron in hydrogen. And bottom line is it's this equation right there. So all of the wave functions satisfy the requirements of that differential equation. All right, so the energies are coming from that. The angular momentum values are coming from that. So L and L sub z are what we call the angular momentum of the different quantum states. Now, what does it mean for, let's go back and talk about energy. What does it mean for the electron to have more negative energy? And what's going to happen is this electron, for the wave functions that are close by, the potential energy will be deeper, and that will give us more and more negative values. It will give us deeper and deeper potential energies. So electrons in the ground state are going to be relatively close to the proton. And then as we go to n equals 2 or 3 or 4 or 5, the electron is more spread out. Now that's something we've looked at with potential energies between charges, and now we're relating it to how the electron wave pattern surrounds the proton. Angular momentum is a little funny. Angular momentum actually has to do with the shape of the wave pattern. So if the wave pattern is perfectly spherical, if it's very symmetric and spherical, that electron has no angular momentum. If the wave pattern has different lobes, we've seen this in some earlier chapters, and we'll see some more examples here, then that wave pattern itself corresponds to a certain amount of angular momentum. Back, in classical physics, back in physics 3A, angular momentum clearly indicated something was going rotationally. But here it's not like there's really anything going on rotationally. It's the shape of the wave function that determines the angular momentum. All right, so let's get to these quantum numbers. N is going to tell us about how much energy each of the quantum states has, and that's a very reliable, accurate formula. The angular momentum is going to make use of two quantum numbers. There's a quantum number L, and there's a quantum number m sub L. And the L quantum number can be plugged into this formula, and it will tell us the amount of angular momentum in terms of h bar. And the convention here is that we leave angular momentum written in terms of h bars. We don't convert that into kilograms, meters per second. We just say how many h bars of angular momentum a particular quantum state has. And so the number of h bars of quantum momentum, of angular momentum, is given by L plus 1 square root. Now, it turns out that in addition to finding out how much angular momentum, there's what's called the orientation of the angular momentum, and that's represented by, by convention, we call it the z component. It's an arbitrary direction that we pick, and we can make measurements of the angular momentum along a particular axis. And that angular momentum actually is an integer multiple of h bar. Okay, so the Schrodinger equation itself provides energy and what we call orbital angular momentum. These wave patterns that the electrons find themselves in, these wave functions, are referred to as orbitals. They're not orbits, they're probability distributions, but we still use the name orbitals to represent them. Now, it turns out that the Schrodinger equation by itself doesn't tell the whole story of the electron. The electrons themselves already possess their very own intrinsic angular momentum that they carry everywhere they go. So an electron, all by itself, has what we call a spin angular momentum. So there is a spin angular momentum of the electrons, and then there is an orbital angular momentum, and the orbital has to do with its interactions with the proton or with the nucleus. The spin is just, the electron just has that. If it's a free electron all by itself, it still carries its spin everywhere it goes. Now, the formulas for spin are completely analogous to the formulas for orbital angular momentum. There's a fundamental area of math referred to as group theory, which is brought in and used in quantum mechanics, and group theory works ideally for identifying for a set of quantum numbers, or for a set of quantum states, what are all the possible values going to be? And it turns out that angular momentum, whether it's intrinsic spin or whether it's orbital, follows the same symmetry patterns, and it ends up with the very same formulas. Okay, what are the possible values here? The energy levels can be defined in terms of the quantum number little l, little n, and they go 1, 2, 3, 4, etc. Angular momentum, you can actually have a 0. So this is a little different. The L can take on the value of 0, but then it continues on as positive integer values. Now this is the total amount, or the magnitude. The orientation, the z component, can be 0, plus or minus 1, plus or minus 2, plus or minus 3. Now, the amount of angular momentum is limited by the amount of energy. So it turns out that L can only be as large as n minus 1. If n is equal to 1, L can only be 0. If n is equal to 3, well, L could be 0, 1, or 2, but it can't be 3 or 4 or 5. So n limits L, and then L limits m sub L. M sub L can only be as large as plus or minus L. And then finally, which means no individual component of angular momentum can be larger than the total amount. Now, spin follows the same rules, except that the spin of an electron is always 1/2. So electrons are what we call fermion particles. They're spin 1/2 particles. They carry 1/2 unit of angular momentum, or 1/2 h bar. Now we can plug into this formula and find out that the total amount is a little bit above and beyond 1/2 h bar. But in the z direction, we either have plus 1/2 h bar or minus 1/2 h bar, and that's referred to as spin up or spin down. All right, and those are the quantum numbers. So every electron in every atom is in a quantum state designated by those 5 quantum numbers. Often, textbooks leave out the S quantum number because it's always the same value. I like including it for completeness, and so that I can see that angular and spin angular momentum, orbital and spin angular momentum, they follow the very same mathematical formulas. So that's it. That's the list of formulas for energy and angular momentum, and all the possible quantum numbers. All right, so you can see it's a lot more complex than the Bohr model. Bohr was able to come up with the energy formula, but that's about it. Bohr did not correctly understand the existence of spin and did not get the angular momentum quantized correctly. It took, once again, that equation, the Schrödinger equation, this one equation, by looking at all the possible solutions to that one equation, gives us all of this information. The spin is an add-on, but everything here is coming from that one equation. So, kind of remarkable. All right, let's see how this could be organized into quantum states. So let's take a look at hydrogen and the possible quantum states. It's very standard, we've been doing this already, to set a 0 level for the energy. So we'll set 0 energy here, and then what we can do is begin dropping down and seeing what's the binding energy for energy level 1, what's the binding energy for energy level 2, 3, 4. We've looked at these numbers. So this is minus 13.6 eV, 13.6 eV of binding energy. This is minus 3.4, minus 1.51, is that right? So we know what these energies are. Now what we're finding in chapter 39 is that in addition to the energy levels, we've got angular momentum considerations. And we can keep track of the angular momentum by labeling different columns in terms of differing amounts of angular momentum. So angular momentum is kind of the new complexity that we're adding to the energies that we've already looked at. So historically, what has happened is the different angular momentum states have been given letters. So L equals 0 is referred to as an S state. Now, this wasn't the original meaning of S, but we now understand that the L equals 0 states are all spherically symmetric, so that works as a mnemonic. So the S states have no angular momentum. 1 unit of angular momentum gives us a set of P states. 2 units gives us D. 3 gives us F, and that pattern continues. Now, the first states, the S, they're spherically symmetric. When I move on to 1 unit of angular momentum, then I get these lobes, a pair of lobes. And then as we move on to more and more angular momentum, the angular shape of the wave pattern becomes more and more complicated. So angular momentum is related to how many angular variations we see in the wave function. So as an example, let's say that I'm looking at an S state. So here's L equals 0. Well, the only m sub L value possible would be 0. And the spin angular momentum is always going to be given by 1/2 total, and then plus or minus 1/2 for individual components. So this is not changing. Now, the spin states, the spin up, spin down, that's always going to be 2 possible quantum states. So what I can do is I can say the orbital angular momentum, there's only 1 possible orientation, but there's 2 possibilities for spin. So if I'm looking at a set of S states, there will always be 2 S states because of doubling up for spin. And there's only 1 possibility for m sub L. If I move on to L is equal to 1, now the m sub L values are -1, 0, and +1. Well, that's 3 possible orientations. And within each of those, there are 2 possible spin states. That gives me 2 times 3. There are 6 possible P states. So S states come in pairs, spin up and spin down. P states come in groups of 6s, spin up and spin down with m sub L -1, 0, or +1, and then the pattern continues. If I go to the next level of angular momentum, there are 5 possibilities, and then 7. So S states 1, 3, 5, 7 possible m sub L's. Each of those gets doubled for spin up and spin down, and that gives us the number of states. In a set of S states, there are 2 possible states. A set of P states, there are 6. A set of D states, there are 10. A set of F states, there are 14. That's all about angular momentum. So what we're seeing is, whereas in the Bohr model we were just thinking of 1 possible energy state, now we're seeing at each level of energy there's a lot of angular momentum possibilities. Many angular momentum possibilities. Well, it starts out fairly simple, but you can see when we get to these higher energies, we're getting more and more possibilities for angular momentum. Now, those numbers seem familiar to me. What about you guys? 2, 6, 10, 14. 2, 6, 10, 14. Where have I seen that pattern of numbers when I'm looking at elements? Well, we'll take a look at that. We've got to think more about that. So the periodic table, when we're looking at hydrogen states, we can already start to see the pattern of where the periodic table is coming from. So this 2, 6, 10, 14, it's a feature of the periodic table. Now what we would guess, maybe our first guess would be this. At energy level 1, we have a pair of S states and the electrons can be spin up, spin down. That's the little diagrams that we draw. The m sub L value would be 0, and there's a pair of electrons. When we move to 2s, it's the very same repeated diagram. M sub L is still 0. 2s, 3s, 4s, 5s, 6s, and so on. And so each of the s states that we come up with, there's going to be a pair of states, and they're going to be spin up, spin down. Now when we move on to the p states, remember this is where L equals 1. Well, now there's going to be groups of 6 states. And the pattern is going to look like this. There are m sub L values of -1, 0, and +1. And for each of those, electrons could be spin up or spin down. So there's 6 possible states for the electron for any of these p states. When I move on to the d, that's going to give m sub L values of -2, -1, 0, +1, +2. Spin up, spin down gives me 10 total states. The pattern just expands for the f's, and we've got 14 states. So again, you can see that the periodic table, all of the elements making up the periodic table, this is largely due to angular momentum, right? It's the angular momentum that's giving us this more complicated pattern of quantum states. Okay, once we've got all of that in place, we're going to come back and look at the periodic table. So we're going to hold off on this. We're following the pattern, the textbook's approach. So the first thing they do is they look at all these quantum states. They identify 2s and 6s and 10s and 14s. We get all the spin up, spin down diagrams drawn, and then we take a break and we go look at something else. We're going to come back to look at the periodic table. So now we're going to move on and say, what about the wave functions in terms of probability? If we square the wave function, that's still going to give us a probability distribution. Now it turns out that if we look at the very, very simplest quantum state within hydrogen, it's the 1s state. It's the state that has the lowest possible energy, and it doesn't have any angular momentum at all, except for the spin of the electron. And the wave function we get for that when we solve the Schrödinger equation for the 1s quantum state of the electron is the normalization constant times e to the minus r over a. So what we're seeing now is that these wave functions drop off exponentially with distance. I'm going to call little a the scaling factor. Now the book uses r naught for that, and we'll see some more examples here where we can make that comparison. My personal preference is to use little a to represent that. That's a constant that we can evaluate. So the probability distribution is going to be the square. It's going to be a squared e to the minus 2, because we're squaring, r over a. So the wave function, as a function of little r, starts off at its maximum value right at the center. I'm going to call that, make a little box here of a, and then we'll put a little box here and ask how much probability and how much here. So what I've done is I've picked little cubic boxes, and if it's atoms, a convenient size to think about would be 1 cubic picometer. An atom is a couple hundred picometers across, and so if I think of individual cubic picometers, these are actually too big. So if I think of these volumes as representing 1 cubic picometer, then if I look at the probability here, that's going to be the very highest for the 1s state. So for the 1s state, the probability is highest at the center, and then it drops off with distance. Okay. Now what you may be thinking is, didn't I hear something different from that in my chemistry classes? And let's move ahead and resolve that. So there's a couple different ways of thinking of probability. If I take equal volumes at point A and point B and point C, I can come up with what's referred to as probability per unit volume. So the probability per unit volume is given by squaring the wave function, and that for the 1s state is just an exponential drop-off. So it says, yeah, the probability in box A is the highest of any of those 1 picometer cubic boxes. Box B is going to have lower probability and box C is going to be even lower. There's a second way of thinking of probability. Instead of saying probability per volume, what we could do is say probability per shell, per spherical shell. So instead of saying point B consists of just that box, what if we say point B consists of an entire spherical shell at that particular value of R? Well, if we include the entire shell, then in addition to the wave function squared, we have to add on a factor of 4 pi r squared. And that changes the probability. So now, this formula, instead of doing probability per volume, it's giving an extra boost if your shell is bigger, right? As you move from A to B to C, the shells keep getting bigger. Now this function right at the center goes to 0. How can it be possible that the probability per volume says the highest probability anywhere is right at the center for the 1s state, but the probability per shell says that probability is 0? And what appears to be a paradox is this is actually going to 0 because we're saying that the R has gone to 0, and so the shell right at the center has no volume. That's why the probability goes to 0. So a better way, again, is I would suggest, the better way to think of probabilities, at first at least, is probability per volume. How does this volume compare with this, where the volumes are all the same size? And if that's the case, then there is this steady exponential drop-off as we move away. Once that kind of sinks in and you're familiar with it, then start thinking about probabilities per shell, and that involves adding an extra factor of 4 pi r squared, and that's going to change, it's a different function. And that says that there's going to be some shell where the total probability for that shell is the very highest. That's how we resolve this apparent paradox. Now this is just showing how to integrate the volume of a sphere. You guys don't have to do that. And so it's a slide showing how to use spherical coordinates to integrate the volume of a sphere. And so I am going to go through this quickly. A sphere can be broken up into r's and thetas and phis in a manner where there's a little bit of volume right there. There's a little bit of volume, dv, and it has dimensions of dr. dr is in the direction of r. And then in the perpendicular direction, there is a distance of r d theta. It's that distance. Here is d theta is the angle in there. And then that gets multiplied by r sine theta d theta. When I multiply these factors together, that gives me something that in the limit of infinitesimals is a cube. And so I can think of a sphere as consisting as a bunch of little tiny cubes. Each of the cubes has this much volume. And then integration will add all those together. Now over here I've ended up with 2 factors of little r multiplied by dr. Those are going to get evaluated between 0 and the radius of the sphere. I've got a factor of sine theta and an infinitesimal d theta, and then I have an infinitesimal d phi. This is going to run from 0 to 2 pi, it's going to run from 0 to pi. When I carry out the integration, I get 1/3 r to the third from here. I get a factor of 2 from the integration in the middle, and then I get a factor of 2 pi, the volume of a sphere. So we can use calculus, we can use integration methods to come up with the formula for the volume. You always wonder, where does the formula for the volume of a sphere come from anyway? Well, this is certainly a derivation right here. Now, when we're calculating probabilities of wave functions, what we have to do is take this volume integration and multiply that by the probability. So for any quantum state we want to look at, we can take this spherical integration and integrate over the wave function. Now, when we're integrating over wave functions, the limits of 0 to 2 pi and 0 to pi still apply, but in the radial direction, in the r direction, we have to integrate from 0 out to infinity. Now, most of the probability is packed within the first, 100 picometers or something, but remember the wave functions are going to drop off exponentially, and that means to capture all the probability, we have to integrate out to infinity. For our finite sphere, we only integrate it out to the radius of the sphere. Okay. Now, in general, wave functions will depend on r, theta, and phi, right? But if it's an S state, then it has no angular momentum, and it has no theta or phi dependence. And that means that for the S states, that reduces down to the wave function of r squared. And that means we can carry out this integration and this one in advance, and that's what gives us the 4 pi r squared. So that's where that probability per shell is coming from. Now, if we carry out normalization, I'm not going to go through the details here. Definitely, if you're interested, stop by office hours, we'll look at it. We can show that for the 1s state, the pattern is e to the minus r over a, and the normalization constant given by 1 over pi a to the third square root. It just is. Here's the Schrodinger equation. So again, the Schrodinger equation in 3 dimensions, px, py, pz, gets replaced by pr, p theta, p phi. If we're only looking at the S states, you can see these things get complicated. So sometimes we just back off and just go to an S state. That means I can drop the theta and the phi's out, and the Schrodinger equation simplifies to this expression. If I follow this pattern of taking derivatives and multiplying, I can show that taking this and putting in some derivatives, plugging back into this formula, again, this is just for completeness. You guys are not required to do these calculations. This formula requires that 2 conditions be met. The first condition is that the energy of the 1s state is given by minus h bar squared over 2ma squared. And the second condition is that the scaling factor is given by h bar squared over m, electric magnetic force constant, times the fundamental charge squared. If I take this scaling factor and evaluate it, it's what is called the Bohr radius. But now we've solved the Bohr radius correctly. The Bohr radius is not a fixed radius. It's a scaling factor for the exponential drop-off of the wave function. So it's a scaling factor, and we'll continue to use that. It turns out that the Bohr radius, little a, is a really handy scaling factor to work in terms of. Also what happens is we now see exactly where the Bohr formula comes from for the energy of minus 13.6 eV. It comes from solving the Schrodinger equation and meeting these 2 conditions that show up from solving the Schrodinger equation. Okay. Very quickly, I guess. When we solve the Schrodinger equation, what we end up with is factors of the wave function cancel out. We're left with the constant E equals this set of constants, and that the 1 over r term here matches the 1 over r term there. So there, you've got a little bit of differential equations that you've taken now. So we just match up the 2 sets of coefficients, and those become the 2 conditions that are met. So the equation requires, if we really have a solution, those 2 conditions have to be met. We can evaluate those to find the energy and the scaling factor for our wave functions. All right, here it is. It's the periodic table. So I almost feel like we took this diversion. Let's go back to here. We were going through all the possible quantum numbers. We were counting up how many quantum states were there. We were getting them all organized. And then we went off and did wave function integrations for a bit. And now we're back to the periodic table. Does that look familiar? Let me see if I have my periodic table with me. Come on, everybody has their periodic table with them that they carry everywhere, right? I don't know. Let me see. Boy, maybe I don't. Oh, here it is. I know where it is. Aha. Okay. So, I know I've got all my credit cards and stuff and my driver's license in here. This is my wallet. And, see, there's the periodic table that I carry with me everywhere I go. So yeah, that periodic, yep, that's it. It's the periodic table. And it all came from solving the Schrödinger equation. Imagine the excitement of physicists back in the 1920s, late 1920s, when they, you know, Erwin Schrödinger established this Schrödinger equation, and they looked at all the solutions, and they go, that's it. It's the periodic table. So very quickly in the periodic table we have different levels. Now what we can do is we can break up segments of the periodic table into different groups of elements as to how the electrons fill within those groups. Now I'm going to go back to this periodic table diagram here. When we say that the electrons fill spin up, spin down, here's some S states, here's some P states, spin up, spin down, spin up, spin down. The reason for this is that, and maybe you've already kind of picked up on this, electrons all have to have their own quantum state within an atom. So if there's a group of electrons within one atom, they can't be in the same quantum state. They each have to have their own unique set of quantum numbers. And so that requires that. And now with hydrogen, that's not such a big deal. In hydrogen, we just have the one electron, and the electron can either stay in the ground state, maybe it goes into some excited states, maybe it drops back down into the ground state. The electron can go into whatever state it wants, but if we put two electrons in there, I can't have both electrons go into the same state. Now, the ground state allows for two electrons, but they can't both be spin up, or they can't both be spin down. The only way they could both be in the lowest quantum state is if they divide into the two available quantum states of spin up, spin down. And as we go through the periodic table, we are the additional electrons have to all find their own quantum state, and that means that they have to work their way through different values of n and different values of angular momentum. And as a result, when we move through the periodic table, we fill the 1s state first. That's hydrogen and helium. Now we know on the periodic table, helium gets listed at the end because it's inert. It's a noble gas. But for what we're looking at right now in chapter 39, it's useful to group the helium with the hydrogen as the two 1s elements. Now, once the 1s is filled, we've got to move on to the 2s, and that allows for two more elements, lithium and beryllium. On the second level, we also have a set of p states. So I got two more, and then 6 more. So on level 1, there's 2 possible quantum states, and when those are filled, we have to move to the next level. Now, there's a bit of a gap from one level to the next, and what that does is, once we've filled 2 electrons, that's a pretty stable configuration. It's difficult to get an electron away from helium. Helium tends to hold on to its electrons really well, but if we move on to lithium, element number 3, it's going to have 1 electron here. Well, that's being held farther away from the nucleus. And that one's not going to have nearly as large of a binding energy. So those outer electrons are going to be relatively easy to become involved in chemical bonding. They can either be ionized or those electrons can join with electrons from other atoms and form new configurations that make up chemical bonds. So chemical bonds are just new shapes for the quantum states of pairs of electrons. Now, the second level has the 2s and the 2p. The third level has 3s, 3p. Just when we were thinking we would get to 3d, it's not there. If we go to the next level of the periodic table, 4s, oh, and now the 3d show up, but the 3d are showing up too late. What's with that? Now, if you're wondering about any of these electron configurations, they're in our textbook. So as any good textbook, physics, chemistry, biology, any good textbook is going to have a periodic table. There is ours in the back. Ooh, that's a pretty well-worn textbook. And down in the details, take a look at the textbook. It's got the electron configuration of each element. Okay, so as individual atoms, it's showing what their electron configurations are. So level 1, 2, 3, 4, 5, 6, 7, they all start off with a pair of s states, but then things get complicated. Instead of going s, p, d, f, the d states get left behind. So the 3ds show up on the fourth level. So all the d states are one level behind where we would have first guessed. The f states are 2 levels behind. Now, it does turn out that this is a pretty reliable pattern, and that the periodic table consists of like 7 rows, and all the elements up through element 118, Osgoody, what's the name of this? Osgoodium? Those have been identified, and the elements that have been identified at the end of the periodic table, they're highly radioactive. They have really short half-lives. So, to a very good approximation, we might say, sure, there could be some other elements identified, but this is a pretty complete look at all the elements in nature. Any elements that are found beyond this are likely to be very, very, very short-lived. And this makes a nice complete pack where we've got 7 levels, and they fall more or less into this pattern. So you can recreate the periodic table, right, from memory, maybe. You just have to remember 2, 6, 10, 14, but the F's and the D's get rearranged. So let's see, uranium, which is element number 92, would be located, let's see, after the first row we have 2 elements. That means helium is element number 2. The next 2 levels have some S and P's. That's 2 plus 6 is 8. That means cumulatively, those would be at the end of rows 2 and 3, elements 10 and 18. These are all the inert gases, all the noble gases, neon and argon. The next 2 rows have S and a set of D's. That's 10 additional elements, plus 6. That gives us 18, so it's elements 36 and 54, which are krypton and xenon, the ones in this last column. And then finally, these last 2 rows of the periodic table, in addition to the S and the P's and the D's, they have a full set of F elements, and that's an additional 14. So 2, 2 plus 6, 2 plus, let's see. Let's do it this way, 2, 2 plus 8, 2 plus 8 plus 8, 2 plus 8 plus 8 plus 18, 2 plus 8 plus 8 plus 18 plus 18, plus 32 plus 32. Those give us the numbers of the elements in that last column. So 2, 10, 18, 36, 54, 86, 118. And then uranium then would be somewhere on this row. Uranium's going to be on the last row because it's beyond element 86, radon. So that's going to be, element 86 has all of these electrons filled, plus we're going to have 2 of these. How many more do we need? We need 6 more electrons. It's going to have 4 of these. And so I've written out the full electron configuration for uranium And the bonding electrons are going to be on the last row. Whatever electrons are available on that very last row, those are the ones that are most available for chemical bonding. Now, in exceptional cases, you can have electrons that are deeper involved in chemical bonding, but for the most part, 99% of the cases, it's just the electrons available in that last row. Now, what's happening with the energy states? In hydrogen, the 3s and the 3p were followed by 3d, but that's not happening through the periodic table. So here's the story. We can take all the elements in the periodic table, all the elements in nature, we can divide them into two categories. The first category would be hydrogen, and then the other category would be all the rest of the elements. So if we consider these to be all the heavy elements that are farther into the periodic table, what has happened is here is the zero reference, the ionization level, and here's a proton, and all of these energy states are the ones closer to the proton, the ones closer in, are going to be lower in energy. But when we get farther into the periodic table, those nuclei have lots and lots of protons. And what lots and lots of protons do is they pull the electrons in closer. So you can just steadily move through the periodic table, and what you find is across the periodic table, each element that you move to, the 1s state is going to be a little deeper in terms of energy. It's going to be pulled a little closer to the nucleus, and it's going to have more binding energy. So the 1s state gets pulled down. Now, all of the other states get pulled down as well. The 1s state gets pulled down the most because it's not being shielded. The 1s state, these electrons are directly, more or less, next to the proton, and so more protons are able to pull those in closer. The 2 states get pulled in less, the 3's less, the 4's less. Now the angular momentum makes a difference. It turns out that the spherically shaped s states get pulled closer towards the nucleus the most. The spherical shape gets drawn into towards the nucleus the most. The p shapes, which have these different shaped lobes on them, do not get pulled in as much. And the d states, which have many lobes on them, get pulled in even less. So what happens then is, once we're into the periodic table, the 1s states are the deepest. That's the first level. The 2s and the 2p are still similar, but the 2s have dropped below the 2p. Everybody's dropped. It's just that the 2s's have dropped more than the 2p's. The 3s's have dropped more than the 3p's. The 3d's have been left behind. The 3s and the 3p and the 3d, which in hydrogen were all at the very same level. The 3s and 3p have been dropped down a lot, the 3d much less, so much so that now the 3d is similar in energy, those electrons, to the 4s and the 4p, and they end up on the same row of the periodic table. Okay, so that's our understanding and explanation for why the d states get left behind by 1 row and the f states get left behind by 2 rows. Okay, and with that, I'm going to say fairly simple correction. We have quite a well-organized set of elements in the periodic table that we can work from. Okay. All right. I'm going to go back and pick up one thing that, it's not very far back. Oh, here it is, just one slide back. So we had mentioned the scaling factor. The scaling factor is kind of interesting because what that's doing is it's telling us how big atoms are. And so the scaling factor, what does it depend on? Well, it depends on the mass of the electron. So this is kind of interesting. If the electron were heavier, atoms and molecules would be smaller. And you go, why is that? And you go, because of quantum mechanics. Because of the way the wave functions would scale with distance, if the electron were heavier, atoms would be smaller. What else could change the size of atoms and molecules? Well, what if the electromagnetic force constant in nature were stronger? What if what if we were able to turn up the electric force? Well, if we turn up the strength of the electric force, if we turn up the K value, A would get smaller. So if we turn up the electric force, the electrons get drawn closer to the nucleus. So it's kind of interesting that along the way, quantum mechanics, the Schrodinger equation specifically tells us how the size of atoms relate to the electric force constant and to the mass of the electron. If those two values were to change, the size of atoms and molecules would be different. All right, let's get some pictures drawn. We've been saying that these 1s states and 2s states and 3s and 4s, they're all spherically symmetric. And so for the 1s state, if we do the probabilities per shell, then we said that the 4 pi r squared wave function squared, has kind of like this. And so we have this one increase in the probability, and then it drops off with distance. Well, what about the 2s state? What distinguishes the 2s? The 2s has a node. So the 2s state, in its probability, has a place where the wave function drops to 0. Now, we saw this before when we were looking at simpler models in back in chapter 38. We saw that in chapter 38, these wave functions were drawn like sine functions. Now, this is kind of similar. What we've got is a wave function that actually crosses the 0. So when we look at the probability, we get a probability of being closer to the nucleus, and then there's a probability of being farther away. These are spherical shells. And then there's a spherical node. There is a node where the probability drops to 0, and it's spherical in shape. So that's what's going on in the radial direction. So when I go from n equals 1 to 2 to 3 to 4 to 5, I'm going to get more spherical nodes. Now, what's happening in the angular directions? Well, if this is the nucleus, and we were going to do a walk around, let's say that we do a walk around from the nucleus. If I do a walk around with an S state probability, I find that the probability has the same value everywhere I go. The wave function has the same value everywhere I go if I'm maintaining a fixed value of r. And what that tells me is I have no angular dependence. It's saying that the angular dependence for this has gone to 0. And I'm realizing I have gone over. We need to take a break here. So I'm going to stop right there, and we'll come back and talk a little bit more about these shapes. Sorry for, anyway, we'll take a break now. So if you guys have questions, stop by office hours. Let's look at those.